We now consider a more theoretical kind of challenge. That's the challenge of improper integrals. We'll define those more precisely in a second, but basically it's an integral that has something, if you like, a little fishy about it, a little suspect, thus the improperness. We'll see how nicely defined they are in our minds, though, before we start calculating and seeing where the mathematical difficulties arise. Let's take this simple example here. A chemical reaction produces a desired chemical at a rate of R of t, something's grams per second. What amount, so amount would be in grams, is produced between t equals 0 and some later time, capital T? Well, the mass produced in grams would be approximately the sum of the rate, which is in grams per second, times some small unit of time, delta t, in seconds. That's how we'd have to use this changing rate with some units of time to get a total mass. We couldn't just pick a particular rate or a particular time, so we'd have to do this kind of sum, and of course we would actually do this in practice with an integral. We'd have the integral of the rate times, not delta t now, but dt, and then we'd bring in the limits. When do we start counting? We start counting at time 0. We stop counting at capital T time, and that would be our integral representing the grams per second times seconds, adding that up over an interval of time. We can actually evaluate this pretty easily. We haven't done exponentials in a while, so this is good practice. We have the integral of e to the minus t, which is the same function again back, except we're going to divide by -1, or turns out same as multiplying by -1. And we're going to have capital T and a 0 here. We sub in the upper, minus e to the minus t, minus the lower one subbed in. This is one of the cases where 0 being plugged in does not give us a 0 value. Have to be careful here. We plug 0 in for little t, we get e to the 0, which is actually 1. So plus 1 because of the double negative. And we'd usually write that, of course, the other way around. 1 minus e to the negative capital T. So that answers the question. What amount is produced between time 0 and time capital T? Well, it's going to be 1 minus this thing here in grams. Well, so what does that mean? Well, one of the follow-up questions we might ask is, what's the total amount of chemical that would be produced if it were run forever? We know there's a diminishing returns happening here. We're producing less and less because the rate is an exponential decay. So in principle, we could say, well, okay, well, 10 minutes an hour, what happens if it runs forever? It's going to give us less and less as we go on. Is there basically a limit to what's going to happen here? And it turns out there is, of course. To run forever would be letting our upper time limit, which was capital T, we're going to let it take the limit as t goes to infinity. So the amount produced as t goes to infinity would be the limit as t goes to infinity of what we found out. We produce 1 minus e to the negative capital T grams, but now we're going to ask what happens when t gets bigger and bigger and bigger. And here we're going back to limits, so review them if you need to. This exponential decay, when we have larger and larger values in the exponent, larger and larger negative values in the exponent, is going to converge to 0. So in the long run, if we let it run forever, we would produce at most 1 gram of material. How does that go back to our earlier example? Well, if we look at the calculation, the bigger t gets, the smaller this term gets, so we're subtracting less, and we basically are left with the 1 gram we would produce in total. Okay, we've derived this and done sort of a limiting idea. How could we have written this question out in mathematical terms to start with? Well, this amount produced over infinite time would be exactly the integral we talked about when we started. We'd have the exponential with a dt, because this is in grams per second, and then we talk about time in seconds. So we have our sum that gives us grams. But if we wanted to do this with the running forever part, what we would do is say we want to run from time 0, and here's the improperness. We're going to say an infinity up there at the top. Now, infinity is not a number. We should treat it with respect and caution, as we're going to see. but this is how we'd represent it in a nice compact way because it happens so often. We'll actually put the infinity symbol up here. Up here and only up here for a second. Let's go to the next page. This is a hard, ironclad rule. If you're writing a test in this course, if you're writing an exam in this course, and you have an integral with an infinite quantity here, this is the first thing you must do. If you have the integral up to infinity, you have to get rid of that infinity and replace it with a number, or a letter in this case here. The idea is we're going to replace the not nice thing with something that's perfectly reasonable, and then we're going to take the limit and see what happens when that variable gets larger and larger after we're done with our integration. What does that mean? Well, if you think of what we're evaluating here, say with that negative exponential curve, we wanted the area underneath that curve all the way up towards infinity. What we're going to trade that for is an upper limit that's fixed. So we're going to say integrate only out to t. That's a perfectly reasonable integral. I can always integrate from a to t. I can always do that, assuming I can do the integral at all. And then we can say, oh, well, once I have the area underneath there and t is just some value in my answer, then we can let t kind of wander out there towards larger and larger values. Oh, how do we do that mathematically? We take a limit. Okay, that's the most common case we're going to look at. It's the most common case, quite frankly, in practice. There are some other cases we're going to look at a bit later, so we might refer back to this. When we have an infinity, the integrand, we do something different. We'll come back to this, though, as needed when we hit it in this unit. The last bit of terminology is, if we take this limit, so we find the integral, the area, up to some boundary point that's finite, so we get an area there, and then we push the boundary further and further by evaluating the limit, and there's two limits. There's limits of integration and the limit as the upper limit gets towards infinity. I apologize. Again, mathematicians sort of missed an opportunity to make that clearer. I'll try to be as specific as possible. But as we take the limit as our upper boundary goes to infinity, two things can happen. We can either get something nice, like we just did in the last example, where we got the 1 gram. The terminology there is we'd say the integral converges. We have an infinite quantity, things can go weird there, but if we do get a nice finite number in the end, the integral converges. If it turns out that we don't get a nice number and that the integral actually goes off to infinity when we look at larger and larger boundary values, then we would say the integral diverges. So converges, you get a nice limit. Diverges when the limit goes weird somehow. And we'll explore that through a series of examples.